Hello everyone, welcome to today's session on magnetic effects of electric current. So in earlier sessions, we learned about the magnetic field effects in current carrying conductor. So now let's see how the magnetic field behaves when it is passing through a straight conductor and also through a loop or a coil and also a solenoid. Okay, so first let's understand how the magnetic field behaves when it is passing through a straight conductor. Okay, so let's look at these circuits here, right? So we have a battery of let's say voltage V, and it's passing through a current I, and we have a switch, and when the switch is on, the I amount of current is flowing through the wire here. So this is the wire, right? Between these two terminals, right? Between these two ends, we have a wire and also a compass, right? And a compass that is placed just below the wire to see how it is deflecting. So when current I is passing through this wire, the straight wire, what is happening is, if you see here, when the current is going downwards, here the magnetic needle or the compass is deflecting clockwise. That means the north pole. So the north and south are deflecting towards clockwise direction. So here it is clockwise direction, the magnetic field is deflecting. And here the same, what we did, we reverse the direction of the flow of current here. Here the direction of flow is from positive terminal to here. Now we reverse the battery. We connected the battery in the opposite way. That means current I is flowing from this side now, right? So here it is in clockwise direction, the current is, and the compass needle is also deflecting clockwise. Now here the current flow is anti-clockwise. You're following, right? So clockwise means how the hands, the minute hand, the hour hand rotate in the clock. So that is clockwise. So this side. And then anti-clock is opposite to that, right? So now the current I is flowing through these ends of the wire in this direction. Here, in this case, it is moving upwards and the deflection is anti-clockwise. So when the current is going clockwise, the deflection of the compass is also clockwise. When the current is being moved in the anti-clockwise direction or upward direction in the conductor, then the magnetic needle is deflecting in the anti-clockwise direction. Okay, so that proves, or we can say that when current is flowing in a direction, the magnetic field is in a particular direction. So when we reverse the direction of current, the magnetic field is also getting reversed. Okay, that's the main observation of this. So basically, what are our observations? Number one, so uh, when when I, that is current, is flowing, right? When current is flowing from north to south direction. So in the first case, right, from north to south, that is downwards, north to south, then what is the needle is then magnetic field is in which direction? Northeast, right? Northeast. That's how it is deflecting, right? Between here and here, between here and here. So this is how it is deflecting. Then number two, when I is flowing, which direction now? South to north, right? The opposite direction exactly. Then what is happening to the magnetic field? So the magnetic field is also, so the magnetic field is in this direction. What is this direction? Here, northwest. It is deflecting to northwest. And also what we have observed, whenever we change the direction of the current, the magnetic field direction is also changing. That is the key observation here, right? This is very important. So what is that? When we change the direction of current, when we change the direction of I, comma, magnetic field direction is also changing, is also reversed. Understood? So basically, it depends on how much current that we are flowing, we are passing through that circuit, and in which direction. So whenever we change the direction of current, the magnetic field direction is also getting changed. Now, the other observation is what happens, like if I am sending 1 amp current, so the deflection is small. When I send 5 amps of current, then the deflection is more. That means the more the electric current that we are passing, the more the electric field that is getting generated. Okay, so I is directly proportional to magnetic field strength. You understood? Magnetic field strength. That means if you supply more amount of current, then more amount of magnetic field. The strength of the magnetic field will be higher. Okay, so it depends on two factors. Based on the direction of the current, the magnetic field direction depends on the direction of the current, as well as the amount of current that we are passing through the circuit. Okay, so that is the behavior of magnetic field when it is in a straight current carrying conductor. Okay, now let's move to how it behaves in a loop or a circular coil. Let's see. Okay, yeah, before we move to that, let's do a clear experiment here, right? On how the magnetic field actually appears through a straight conductor. So here, if you see in the circuit here, we have a battery and the current I is flowing here. We have a variable resistors to increase or decrease the amount of current that can be supplied. And then we have I amount of current passing through the straight conductor XY. And we have a plane of paper and also a compass to draw how this is looking like, to draw the magnetic field lines surrounding this. So we already learned that the current carrying conductor forms a magnetic field surrounding it. So how it is forming is, it is like a concentric circles. So for a straight line or for a straight current carrying conductor, the field is, the magnetic field is formed in concentric circles. So we learned about bar magnet, right? For bar magnet, it is coming in a particular shape. But for a straight carrying conductor, the field is formed in concentric circles. Okay, you see, the field is forming surrounding this straight conductor, and the strength of the field will be highest at the near to the current carrying conductor, and as we move away the strength becomes reduced. Okay, so that's the observation we can do. So if you look at this, right, the bottom diagram, if you see a pattern of concentric circles indicating the field lines of a magnetic field around a straight conducting wire. So if we actually see like how this magnetic field is forming, this is how it will be. The bottom diagram shows the arrow in which the circles show the direction of the field lines. So if you see here, the field lines are in this direction here. You understood? So the field lines are forming in this direction. That means this is in clockwise. The field is in clockwise. But how to know like in which direction the field will be, the magnetic field will be? We know it is in concentric circles, right? But which direction? So that we can derive using a rule called right-hand thumb rule. Okay, in a straight current carrying conductor, to find the magnetic field direction, we can use right-hand thumb rule. Okay, so what we can say using right-hand thumb rule is, so if you hold your hand like this, right? Like you can see in the diagram as well. You need to hold the wire. It's an you feel like you are holding an wire, and your thumb should show the direction of electric current. So for example, if I hold like this, the curled finger, the direction of the curled fingers show the direction of the magnetic field. So if the current is going up, right? If the current is going up, then the direction of magnetic field will be in this direction. What is this direction? Anti-clock. Understood? And if the current is going in the downward direction, then the magnetic field will be in the direction of my curled fingers. So what is the direction of this curled finger? That is in clockwise. That's what it is being shown here. So there is a rule which can be used to find the direction of the magnetic field in a straight current carrying conductor. So if you see in the diagram here, the current is going in the downward direction. The thumb should indicate the direction of the current, and the curled fingers indicates the direction of the magnetic field. So here the magnetic field is in clockwise direction. Understood? What happens if the current is going up? Then our you need to use right hand thumb rule, right hand thumb rule, and your direction of the magnetic field is towards the curled fingers. That is our anti-clockwise direction. So my magnetic field will be like this, right? And it will be in this direction, that is anti-clockwise. So when in the exam, if they ask about right hand thumb rule, explain right hand thumb rule, you can just draw these two diagrams stating that the thumb should point to the direction of the electric current, which is, if it is downward, then the curled finger direction shows the direction of the magnetic field. So, and you can just draw this diagram. So when we point right hand thumb, that is important, guys. Okay, when we point right hand thumb in the direction of, I'll just say I, electric current, then the curled fingers, the curled fingers direction indicates the magnetic field direction. Understood? So that's about our right hand thumb rule. Current through a horizontal power line flows in east to west direction. Okay, so let's draw this simple east-west direction, right? So this is east, this is west, and this is north, and this is south. So now what they are saying, a current through a horizontal power line flows in east to west direction, right? So let's say this is east and this is west. So how the current is flowing? Current is flowing from east to west, right? East to west. What is the direction of the magnetic field? At a point directly below it and at a point directly above it. Okay, so for example, let's say what is the the direction of the current here up at this point, for example, let's say at point A, and also below that, let's say at point B. Now, what happens? Using right hand thumb rule, I can place the right hand thumb rule like this because the direction of the current is from east to west, right? So now in this direction, I have the current flow. So my curled fingers are in this direction, right? So that means, so for example, if the current is flowing from, right, if a wire is there and the current is flowing from this to this, then the curled finger indicates the direction of the magnetic field. So if I draw that, right, so I can draw an imaginary circles here. So in this direction, and what is the direction of magnetic field? It is in this direction, upward direction. That means it is in this direction. Okay, you understood? This is how I can curl the fingers, right? So if you look from here, right? If you are looking from here, right? For example, if you are looking from here, that is from east side, what you can feel, this is clockwise. Understood? This is clockwise. If you are looking from here, then this is like opposite, so anti-clockwise. And at this point, if you see the direction, so the direction of the magnetic field depends on from which side that you are observing. So if you are observing from the east side, you can feel that the magnetic field is in the clockwise direction. And if you look from the west side, you can see that the magnetic field is in the anti-clockwise direction. Okay. So the right hand thumb rule basically states that when we point right hand thumb in the direction of the magnet, in the direction of the electric current, then the direction of curled fingers indicates the magnetic field. Okay, that's about right hand thumb rule. And we have also seen how that can be used in a horizontal wire, right? When a power is carried through a horizontal wire, if we point the thumb into that direction, then the curled fingers indicates the direction of magnetic field. And the direction of magnetic field changes based on the side from where you are observing it. So if you are observing from the east side, it is in clockwise. And if you're observing from the west side, then it is anti-clockwise. So that's about right hand thumb rule. Now, we just, so far what we learned about the current in the straight conductor. Now let's move to coil or a loop, right? So magnetic field in a coil. So coil is basically a ring, a circular ring. Okay, so that is made of, for example, copper, right? A copper wire is bent into a circle, for example, the above diagram here. So when current flows through this, right? When current flows through this, so here the current is flowing into the coil and going in this direction, right? The current is going in this direction and getting exited from here. You following? Right? So the current here is going in this direction. So again, here if you see from this side, it is anti-clock, and if you look from the other side, it is clockwise. So here, if you see, we know that during the magnetic field formed when a current is carrying, it is in the concentric circles, right? So at one point, you see here, it is in concentric circles, right? At every point, if you see a set of concentric kind of circles are formed at every point. Now, if you look at overall, this is how you will see at the top portion, and this is how we see at the bottom portion. And at the middle, we see uniform magnetic field moving from south to north, this direction. Okay, that's what we observe when the current is flowing through a magnetic coil. Okay, into a coil. So what is the how we can find the direction? It is same, right? So if say the current is flowing like this, then the direction of magnetic field is in this direction. Okay, now this is with one coil, right? So what if I combined n turns, right? One coil is producing certain magnetic field. Now if I combine n coils, right, n turns, the copper wire I have turned n times, right? Like 100 times I have turned it. Now there are 100 coils. So what is the behavior of the magnetic field? That is what the bottom figure explains. So you have connected to a battery and the current is being passed to that in the which direction? Anti-clockwise direction if I am seeing from this side. Then the magnetic field at these points, A and B, these are the 2 points we are observing, and this is like this, and at the center there is an uniform magnetic field here. If you see at the center, this is like a straight line, and that's the uniform magnetic field. So why we need to combine these coils, right? So if you know electric motor, so if you have ever seen electric motor, there will be number of coils turned within a magnetic field. Okay, so what happens is when you have number of coils turn and an electric current, when we power on, the current flows through all those coils. When the power flows through those coils, it generates magnetic field. When the magnetic field is generated, and if it is placed within the magnet, right, that is what we will learn now. So we have a magnetic field here produced by the current carrying coil, and if that coil is placed in between the magnet, right, let's say I have a magnetic field here, let's say south and north, and I have these coils, right? N coils. And there is an axle here, something, right? And when I'm passing a current I into these coils, surrounding it, it produces magnetic field, right? So when this is already in a magnetic field, basically what happens, they repel each other, right? They repel each other, and the net effect is it creates some push. So the coil is continuously producing magnetic field, and the magnetic field lines of the magnets, that is from north to south, right? This is how the magnetic field will be. So when this magnetic field cuts the magnetic field that is produced within the coil, it generates a force. That force is nothing but the rotary motion. That's how, for a fan, if we on a fan, right, what happens is there will be a coil, that electricity, that coil generates magnetic field, and if that magnetic field cuts with the magnetic field, that's where it produces a motion that can be a clockwise or anti-clockwise rotation. So that's how the what motor is useful is, the motor converts electrical energy, right, electric energy into mechanical energy, which is the rotation of the fan, or rotation of the motor, or rotation of the vehicle wheels. Understood? It's converted into mechanical energy or rotary motion, we call it as, right? So these are the examples, like electric motor is one example. And if we do the reverse to the electric motor, that is uh, a generator. So that is called, this is, that is called electric. Uh, so do you know what is electric generator? So in electric generator, mechanical energy is converted into electrical energy. So this is exactly opposite to the motor. So in motor, what we are doing, we supply the power and it gives the rotary motion. Here, using the diesel or any other means of energy, we supply a rotary motion, right? So when a generator, when we need to on the generator, we put the fuel and we give the mechanical motion. When it starts giving the rotary motion, the exactly opposite happens, right? So here, exactly the coil is being rotated in between the magnetic field, and that produces the electricity, right? When we pass the electricity, it is giving the rotary motion. When we do the reverse, it gives the electric current. So these two are key applications of coil. So where coil is used in electric motors and electric generators. Okay, so basically what happens in the coil, a coil produces a uniform magnetic field at its center. Okay, so that magnetic field, when cuts with the magnetic field supplied within the by the magnets, right? Then it produces a force. That force gives the required motion. Okay, so that's about the coil. Now let's look at solenoid. What's a solenoid? Solenoid is just like a spring. If you see here, it is like a continuous coil, right? A coil is one thing, and number of coils is number of rounds. Here, it is a continuous coil in a spiral way. It's like a spring. Okay, we have seen the spring, right? So basically, what's a solenoid? This is the solenoid. A solenoid is kind of a spring, and it has, it is a continuous coils actually. right? So when we connect these ends to a battery, right? When we connect these ends to a battery, this is the plus and minus terminal and the current flows through that. So what happens here, it acts like a bar magnet. When current passes through a solenoid, it acts like a bar magnet and it produces highly strengthened magnetic field at its center, right? So it produces high intensity or high strength magnetic field at its center. If you see here, this is uh, the 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 strength of the magnetic field is very high at the center of the solenoid. So this is where it produces the highest magnetic field strength. So that we can use to magnify, right? So magnetize different metals or different materials. So for example, you would have heard about electromagnets, right? So what is an electromagnet? A current carrying solenoid coil is used to magnetize the steel rod inside it, and that is nothing but a electromagnet. Electromagnet is something which is inducing the the magnetic strength, and it can be used whenever we need. Okay, a bar magnet is nothing but an electromagnet, right? So like that, so the application of solenoids is we can give an uniform magnetic field at the center of the solenoid, and that magnetic field can be used. It is very high, so that it can be used if we keep any material which can be magnetized and can form into electromagnets. So it can induce magnetic characteristics into that metal. So that's the application of solenoids. So the field lines of the magnetic field through and around the current carrying solenoid. So it basically, the observations we can write is solenoid, solenoid behaves as a bar magnet because the magnetic lines are in the exactly the same way how we draw for the how how we observed for bar magnet. So solenoid behaves as a bar magnet when current is passed through it. Understood? Passed through it, and it has yeah, it produces high strength, high strength magnetic field, high strength magnetic field at the center of it. At the center of it. And also this field can be used, this field can be used to magnetize, right? To magnetize soft iron, gamma steel, etc. Okay, so the key benefit of solenoid is we can produce high strength magnetic field that can be used to magnetize few metals like soft iron or steel like that to produce electromagnets. Okay, all right. So that's all for today's session. So thanks for your time, and I'll see you next time. If you have any doubts, you can contact me using my Urban Pro profile. Thank you.